to the year.
All right, everybody. This is going to be our last topic lecture in CE 414. Friday, we have our exam review, but this is it. This is not only our last topic, but that right there is our last homework. The last homework, besides the day due Friday, that's it. Other than the course eval, if you upload proof of your course eval, you get 10 bonus points. One thing I'll say is that I checked, 15 out of 21 students had completed the evaluation, but only 13 had uploaded the proof. Again, you say that I'm the worst professor ever, but if you upload that proof, those are free bonus points, so definitely do it. Now, I don't know, does the survey close on the 18th or the 25th? I don't remember. 20.
I think it's Friday.
Or sorry, 21st. Oh, why not say? Yeah. So yeah, Friday's the 21st. Yeah. So you need to have your course eval survey done by Friday, because that's when it closes at the university. But the 25th is our, I think that's when our Tuesday final is. So that's why I had that due. But if you just upload proof that you did it, again, 10 free bonus homework points on top of your homework average. 6.7 is being graded, 6.8 is due today, and homework 7 is assigned today, due Friday. Now I'm going to give you the solution to homework 7 on Friday, so I'm not accepting late homework for homework 7 because the moment that you turn it in, the solution will be free, be available. So, but that's basically it for steel design other than the celebration next week. So, sound good? All right. Like I said on Monday, this is sort of the end of the class, and the purpose of today's lecture, or this week, is tying up loose ends. And the first thing that we did on Monday was we discussed how to compute shear capacity, because we had been sort of just relying on table 3.2, and I said, no, y'all need to at least understand how to do it. Now, what we did on that last homework assignment was it required you to review the specification in a bit more detail than me just sort of regurgitating it to you. Hopefully that went well. I don't think that assignment was too complicated. Should have been pretty brief. I'm going to go through a little bit of that today, a little bit more of that today with local buckling. But let me sort of set the stage for local buckling. And I want everybody to go back to the column curve and the beam curves in your head. So with the column curve, one of the things I want to recognize with the column curve is that there are two zones. There's either an inelastic buckling zone or an elastic buckling zone. And there is a singular limit that defines which zone that you're in. And with beams, there are three zones. There's full plastic moment, there's inelastic LTB, and there's elastic LTB. And for those three zones, there are two anchor points that define what zone you're in. Now, both of these curves, assume a global buckling mode. And today, what we're going to discuss is local buckling. Now, while local buckling and global buckling are different, there are analogies to how they're handled, global versus local. There are analogies. Now, just to make sure everybody's on the same page, what we're talking about in local buckling land is when a given element of a cross-section fails before the whole thing does. So I have here a picture of an image in the real world where you can see this, these flexural elements, and you can see that the flanges have buckled. You can see the flanges have buckled here. This would be an element where the flanges buckled before the whole thing did. A analytical model, I believe this was an abacus model, but kind of shows this in a maybe a more academic view. But you can see, so here I have a column. This column over here on the right is experiencing global buckling. The entire cross-section is translating from the left to the right. Whereas over here in this left image, you can see that the individual elements, the flanges and the webs, are sort of crinkling, if you will. And this is an example of local buckling. Okay. Now I'll level with you that local buckling is not as much of a primary concern in building design than it is in bridge design. Because in bridge design, mostly what we're doing with flexural elements is we're either using really deep rolled beams or we're using plate grooves. Okay. So, for example, the really big bridge that got constructed along Interstate 64 near Exit 45 in Nitro, that was the longest single plate girder span, I believe, in the United States, because it's like 560 some feet long. Those girders are not W shapes, okay? Those are plates that have been welded together. The structural engineers in charge of that project tailored those plate sizes to meet the load demands of the structure. And if you, as an engineer, are playing around with plate sizes and plate thicknesses and things like that, well, then you really got to make sure that you're accounting for local buckling. So whenever you're detailing plate girders for highway bridges, all that local buckling stuff that we really haven't been talking about this semester for building design suddenly becomes a really big deal in bridge land. Now, this is a topic that's pretty near and dear to my heart. This was actually something that I needed to address for my PhD work. Now, I don't show this, I don't put this up here to just start showing off everything I did for my personal research, but I'm showing this because this actually helps make the case for how the limits are derived, okay? So basically what we do when we look at local buckling limits in the specifications is what we're trying to see is so we're trying to compare the width to thickness ratios of the plate elements, and we're trying to compare those against specified limits. So we actually already got a slight taste of that when we looked at shear, because if you remember on the shear homework, what we were doing is we were taking the width to thickness ratio of the web, we were taking that H over TW ratio for the web, and we were comparing it against some limits. Like for the shear homework, we were looking at, what was it, 2.24 times the square root of E over Fy, and seeing whether that web slenderness was bigger than that or smaller than that. And we were using that to help determine capacity. It's sort of the same thing with really any local buckling limit. Usually what we do is when we try and develop these limits is we look at the width to thickness ratio and we sort of figure out what does that ratio need to be in order for the buckling stress to be equal to the yield stress. And that's where the limits come from. So like what I did for my PhD work is I was looking at a cold vent press brake form tub girder, and what I was doing was I was running a series of local buckling analyses, and I was trying to figure out when the girder would locally buckle, okay? And what I found is based on the configurations that I was working on, that here was a buckling curve for this girder, and I found that it would buckle when the moment hit, or it would buckle in a local mode when the moment hit about 1.52 MY, which was 50% higher than the yield moment. So what that told me was, based on this configuration, local buckling really wouldn't be a problem. Local buckling would be a problem if this buckling moment happened below MY, but it's not happening below MY, it's happening a whole lot above MY. So that told me as the engineer, I don't have to worry about local buckling. Now, what we do in AISC is, if we are going to consider local buckling, what we do is we look at the individual plate elements, we look at their slenderness values, and then we compare that against the codified limits to see whether or not it's going to matter, okay? Now, in the spec, AISC differentiates between two different types of plate elements. We call those stiffened elements and unstiffened elements. Now, the difference between a stiffened element and an unstiffened element is how many supports there are. So for example, if I'm looking at an I-shaped cross-section like this, a stiffened element would be any element that's supported on both sides. And so that would be something like the web of an I-section, the web of a channel, something like that. An unstiffened element is any outstanding plate element that's supported on one edge. So an unstiffened element would be like this outstanding flange here, the leg of an angle, the stem of a T-shape, anything that's outstanding, okay? And what we do is that for each of these elements, we compute a slenderness being a width to thickness ratio. So for the web, what we're interested in is we're interested in the height divided by the thickness. For the flanges, what we're interested in is the width divided by the thickness, but we're only looking at half the flange. We're only looking at this width divided by this thickness, which is why The slenderness limits that you look up in the spec will say BF over 2TF. That's why there's a 2 there, because we're only looking at half the flange. And these slenderness values are so important that they have been pre-computed for you for every W shape and any relevant section inside the manual. So what we will do in the spec is call these lambda values. So this is like lambda sub F for the flange, lambda sub W for the web. With me so far? Okay. Now, what we need to do for a given W shape, in order to see whether or not local buckling is going to be a problem, we need to classify this section, okay? Now, for columns, we have 2 classifications. We have whether or not, oh, that's a typo. Sorry, I just noticed a typo. Look at me. Let's fix that right now. This is the columns. Ooh. Let's redo that. Okay. So what we need to do is we need to classify our sections according to whether or not local buckling is going to be an issue. Now, if you remember with the column curve had 2 regions. It was either a zone 1 or a zone 2. Well, for local buckling, there are 2 classifications. It's either going to have slender elements or not. So for columns, we say that if the elements are stocky enough, if they're stocky enough that local buckling isn't going to be an issue, sometimes we'll say that's non-slender, sometimes we'll say that's compact, okay? So basically what we're checking is whether or not the slenderness of the flange or the slenderness of the web is less than or equal to some limiting value, which we'll call lambda R. If it's bigger than that, then we'll say it has slender elements. And I'll show you if local buckling is an issue, generally how you would compute the capacity. And it's really not all that challenging, just maybe a little bit more math. For beams, if you remember with beams, we had 3 regions of lateral torsional buckling, a zone 1, a zone 2, a zone 3. Well, for beams, we have 3 classifications for local buckling. We either have compact, we have non-compact, we have slender. For the entirety of this semester, we have been assuming that all of our beams would be compact and all of our columns would be non-slender. So now what we're going to do is go back and see whether or not those assumptions were valid. Now, in order to classify these elements, you need to know what these limits are. And these limits are found on page 16.1-16. So this is 16.1-16. Everybody should sort of turn to that. This is a pretty straightforward exercise to classify an element. We'll look at how capacity works here in a bit. But if you notice, 16.1-16 has a really big table on it. The table actually extends across a few different pages. So there's a B41A and a B41B. B41A is the width to thickness ratios for members subjected to compression. B41B, the width to thickness ratios for members subjected to flexure. Okay? So the first table is for columns. The second table is for beams. Okay? With me so far? Now, I want to look at table B41A because I kind of want everybody to pay attention to this. It's a little hard to read, but if you look over here on the left, so see how there's a series of cases and there's 9 cases? Y'all see that? So there's case 1, case 2, case 3, case 4. Case 1 through 4, if you look at the very, very left, it says unstiffened elements. So unstiffened elements are any element that's outstanding by itself, whereas stiffened elements are ones that are supported on both sides. So if we're looking at a W shape, what we're looking at is case 1. So case 1 is looking at the flanges of rolled eye sections, and our limit is 0.56 square root of E over Fy. Whereas for stiffened elements, we're looking at H over TW for case 5, and we're looking at 1.49 square root of E over Fy. So all we have to do is compute these limits, compare them against our slenderness criteria for our columns and beams, and see where the shapes shake out. So what we're going to do, just to make sure how this works, is we're going to classify a W14 by 99 according to local buckling in both compression and flexure. And then I'm going to sort of show you with this section what happens, how do you handle the capacity if you start failing one of these limits. And if you fail one of these limits, if you have an element that's slender or non-compact, it does not mean that the column explodes when you put a feather on it. What it means is that the capacity has to be reduced in order to account for the fact that local buckling might occur, and you just need to do some more math. It's really not all that more challenging, and you'll see that here in a bit. Okay. All right, so once this decides to load, there we go. Okay, so what we're going to do is we're going to classify a W14 by 99 with 50 KSI steel according to local buckling. Okay, now in order to do that, what we need to do is for a W14 by 99, we need the lambda F and the lambda W, which, just to make sure that this is clear, this is BF over 2TF, and this is H over TW. So let's look these up. So for a W14 by 99, what is the flange slenderness and what is the web slenderness? .34, and what about the lambda W? 23.5. And just to make sure that everybody is clear, what are the units for these numbers? There are none. These are unitless. Slenderness properties are unitless. Okay. All right. So the first thing that we're going to do is we're going to classify this element according to compression. Okay, so in order to classify according to compression, what we're doing is we're going to table B41A on page 16.1-16. And let's see what cases we need to look at. Okay? So let's everybody turn to B41A. So I'm on 16.1-16 or 16.1-17. And what we're going to need to do is we're going to need to classify both the flange and the web. Okay, so let's classify the flange. Okay, so let's make sure everybody's paying attention. Is a flange an unstiffened element or a stiffened element? Unstiffened, okay? So if we look at our unstiffened elements, which case is going to apply to a W section? Is it going to be case 1? Yeah, it's case 1, right? So case 1 tells us that our limiting value, so first off what we're going to do is we're going to say BF over 2TF is 9.34, and our lambda R, in this case I'm going to call it lambda R sub F for a flange, and how do we compute that? It is what? If we're looking at case 1, what is that? There we go. And that format, like a number times the square root of E over Fy, should be something we're pretty familiar with, because that, remember for columns it was 4.71. So .56 square root of E over Fy, so 0.56. So what do we got for this? So what do we have here?
13.49.
13.49. Do I have a second?
Yes.
Okay, so I want somebody to help me out with this. What do you think this means? Do you think this means that our flange is slender, or do you think it means our flange is compact? Like, do we have a stocky flange, or do we have a flimsy flange? Well, let's think about this. This 9.34, that is a measure of how flimsy our flange is, right? And this is a slenderness, right? The bigger the value of slenderness, the more flimsy it is. So this is a measure of how flimsy our flange is, and this is the limit to determine whether or not it's slender or not. So do we have a compact flange? Do we have a slender flange? Compact. That's exactly right. Because what we've got is we've got that our BF over 2TF is less than lambda RF. So what this means is that we have a compact flange under compression. So that is one of our answers. Okay, this is a compact flange under compression. All right. What about the web? Okay, so the web, what we're going to do is we're going to say H over TW, which is H over TW was 23.5. And what about lambda sub RW? So what case are we going to be going off of in table B41B? So is the web an unstiffened element, or is it a stiffened element? Stiffened, okay? And so what case are we going to use? Case 5, right? Case 5 is the web of a doubly symmetric, rolled, and built up I shape. So that's exactly what we're looking at here. And what is our lambda R going to be for the web? It's going to be what?
1.49 times the square root of the overflow.
And what is that if I have 1.49 square root of E over Fy? $35.9. Do I have a second? Okay, so H over TW is also less than lambda RW, so what does that mean? That means we have a compact web under compression. So, just so you're aware, what this means is that if you remember earlier in the semester when we looked at columns, we didn't talk about any of this. Well, all that math that we did earlier in the semester assumes that the flanges and webs are compact. For a W14 by 99, that assumption is in fact true, that they are compact. Okay? What I'm going to show you is how does that work out in the specification here in a bit. So just bear with me, but we're gonna look at that here in a bit. Okay. So now what we're gonna do is we're gonna classify according to Flexure. So now we're gonna do this again, but we got a little bit more going on. Oh, sorry, I'm repeating myself. So for the flange, again, we've got our BF over 2TF is 9.34. But now what's going on with bending, okay? If you turn the page and you go to the bending chapter, now we got a little bit more going on. So first off, when you turn the page, there's two tables, right? The table on the left is for unstiffened elements. Table on the right is for stiffened elements. And what happens is we have two limits. We have a lambda P, we have a lambda R. So what I'm going to do is I'm going to compute both of them, okay? And you'll see where this shakes out. So we'll call it lambda PF, lambda RF, okay? And what we have is we have what? Y'all see 0.38 square root of E over Fy, and you have 1.0 square root of E over Fy. Y'all see that? It's in that first case. Because remember, with beams, we have three zones. We have compact, we have non-compact, and we have slender. Everybody see that? Now, what happens here? Okay, so what happens when we compute lambda PF? Can somebody go ahead and check that one out?
.15.
9.15. And what about lambda RF?
24.1.
24.1. All right. Seconds on these? So, now I want somebody to help me out looking at these categories. I have compact, non-compact, slender. How do you think you would classify this flange? Which one would it be? Would it be compact, non-compact, or slender? It'd be non-compact, it'd be in the middle, right? Because if it was smaller than this, it'd be compact. If it was bigger than that, it'd be slender. It's in the middle. So what we have is we have our lambda PF is less than BF over 2TF. That's less than lambda RW. So we're in the middle. So the way that we would classify this is a non-compact flange under compression. Or under flexure. Or if you want to write this, you can say under bending. However you want to write it.
That's supposed to be RF, right? And RF.
Yes, it is. You're right.
That's like 2 today.
I know. But here's the thing. It's like the meal points. Like I'm near the end of the semester. I'm only allowed 7 mistakes a semester. I've been doing pretty good. I need to start racking them up. You know?
Oh, okay. I use them all.
So these are on purpose.
So they don't carry over.
Of course they are. You know.
They don't carry over.
What's that?
So they don't carry over to the next semester.
No, they don't.
No.
I don't have rollover mistakes. So I love my job. All right. So for the web, we do something similar. We have H over TW equals, what was H over TW? 23.5. And then we're going to have a lambda PW and a lambda RW. So in this case, what we're going to do is we're going to look at the table to the right. And what do we have for the table to the right? What are our lambda PWs and RW? So there's square root of E over Fy, but the numbers are different. So what do we got for lambda PW? What's the number? 3.76. And what about lambda RW? 5.7. Okay. All right. I'll go ahead and shut these out for you. So you get 90.55 and you get 137.5 0.3. So how would you classify the web in this case? Compact. This is a compact web. Okay. And so this is what we mean by classification. So H over TW is less than lambda PF. I'm going to show you a few things because I've got, I guess.
Dr. Mike. Isn't that supposed to be PW?
It is. I'm racking them up. I'm racking them up. I was getting ahead of myself. I was thinking about what's going on in the manual. Getting ahead of myself. Man, I better calm it down. I need to calm it down. Next thing you know, it'll be concrete design. I'll start throwing some FC primes up there just for the heck of it. So. Here's a stress block, 0.85 FC prime, you know. All right. Okay. All right. I want everybody to follow along with me for a few things because I kind of want to show you some stuff. Okay. First off, does anybody have any questions? Okay. I want everybody to turn with me in the manual to a few different sections. The first thing I want you to do is I want you to turn to table 1-1. I want you to find the W14 by 99. Anybody notice something on the label?
Got a little F.
A little F. What does that F mean? Well, what does it say on the bottom of the...
It exceeds the compact limit for Flexure with FY equals 50 KSI.
That's exactly what happened, right? Now, the manual doesn't report whether it's the web or the flange, but it does tell you that this shape is one that is subject to local buckling. In fact, if you start looking at other shapes, you will see notes like a V, a C, etc. And that's what those limits are telling you. They're telling you that for the common grade of steel for 50 KSI. That doesn't mean that you still don't need to do this because in order to compute the capacity, you actually end up needing these values, and I'll show you that here in a bit. But now you kind of know what those notes mean, okay? All right, with me so far? All right, I want to show you something. Okay. Now, I want you to follow along with me in the specification because now I want to go back to some sections in the spec and I want to investigate them a little more thoroughly. Let's start off with Chapter E. I want everybody to go to Chapter E. So we're on 16.1-33, and then specifically we'll be looking at the next page, this user's note. Well, let's go to Chapter E. Okay, so this is Chapter E. This is the chapter that tells you how to design members for compression. This is the column chapter, okay? So if you notice, so the general provisions tell you, okay, here's the fee value. We know fee is 0.9. But what I'm interested in is now taking a look at this user's note. Okay, so this is something we really never paid attention to so far, but I think this is probably one of the coolest, or the most useful introductions in the most recent editions of the manual. So this is user note for for Chapter E. What it does is it helps you determine what section of the specification you should be using. So for example, we have a cross section, okay? So let's look at the different types of cross sections. So we have an I shape, we have I shapes that are singly symmetric, we have channels, we have tubes, etc. What it's telling you is, okay, if we have compact elements, here are the sections in the manual that we need to address. So if we're looking at this, we need to look at section E3, we need to look at section E4, and we need to look at these limit states. We didn't look at torsional buckling, but torsional buckling never really governs for W shapes. We just didn't really worry about it. But if you have slender elements, it doesn't mean that the column explodes. It just means that you need to look up, or you need to compute the capacity according to a different section in the manual. So let's just say, so RW14 by 99, what was it? It had compact flanges and webs according to compression. So we're here, we go to section E3. What does section E3 look like? Well, let's go to section E3. So here's section E3, and here's the capacity. Section E3, flexural buckling of members without slender elements, and here's the math. Does that look familiar? Those are the column curves, right? What this is saying is that we do not need to consider local buckling because we have compact flanges and webs, so we just compute the capacity assuming that global buckling occurs, which is the same column curves we've been using this whole time. Okay? Make sense? All right, let's continue flipping through the manual. Let's go to 16.1-45. And let's look at the beam chapters. This is chapter F. Okay, so we're in design of members for flexure, and just like the previous chapter, we've got a nice little user's note that looks like this. So we got different sections in the manual. Now look at this. This chapter is laid out a little differently. Okay, so we've got the different sections, the different cross sections that we're looking at, but then look at the flange slenderness, the web slenderness. Okay, so this problem that we just did, what did we have? We had a W14 by 99. The web was compact. What was the flange? Non-compact, right? Is that what we got? Okay, so let's look at section F3. So F3, we have a doubly symmetric eye shape. We have a non-compact flange. We need to be using section F3. And what it tells us, what are the limit states that we need to consider? Well, we need to consider lateral torsional buckling, which is what we did before. Then we need to consider FLB. What is FLB? It stands for local buckling of the flange, or flange local buckling. Why are we considering the flange? Because the flange is the one that's flimsy, right? So let's turn to section F3. See what it looks like. Okay, so here's section F2. Section F2 contains all the stuff we've been using before, right? Here's all the FCR stuff, the zone 2 curve, all that stuff we looked at before. And here's section F3, 16.1-49. Okay, what do we have here? Doubly symmetric eye-shaped members with compact webs and non-compact or slender flanges. It's exactly what we're looking at on this problem. Look at this user note. The following shapes have non-compact flanges for FY 50 KSI. Look at what we got. Oh, look at that. Look at the W14 by 99. That's what we just looked at. It's like I just picked it out of the clear blue sky. I just got lucky. I'm good like that, right? So how do we compute the capacity? How do we compute VMN? All right, the nominal flexural strength shall be the lower value obtained according to the limit states of LTB and compression flange local buckling. So what do? We take this W14 by 99 and we compute two VMNs. The first VMN is everything we did, for the past couple weeks. So go to get a VBF, get a VMP, go to the ZX charts, all that, and get the VMN according to that section of the manual. Then the next thing that we do is we compute the capacity according to this. So we have a non-compact flange, so how do we compute the capacity? We use this equation right here. So what do we need in order to do this? Well, we need, what about over here? So we need lambda PF, and RF. Do we have those values? It's like we just computed them. What about over here? 0.7 FY SX. Can we look up SX for W14 by 9? Of course we can. What about MP? How do we compute MP? Don't remember how to do that? How do you compute MP? You take Fy and you multiply it by what?
FCO. Sorry.
We're going to be celebrating this in next week. So how do you compute MP? Fy times what? This was a few weeks ago. ZX, right? Yeah, that might show up on the celebration. Just a heads up. All that ZX stuff, that might show up. So what we would do is we would compute our capacity according to the previous method, and then we can compute our capacity according to this expression and just take the minimum of the two. Is that really all that difficult? Pretty straightforward, right? So I'll tell you, if you do that for this problem, you get a VMN of about 645.8 foot kips. You ought to try it out just to see how well it works, but this isn't really all that challenging. The other thing I gave you was in your online, this is on Blackboard, I prepared this. This is a column capacity. I'm not going to go through it in super significant detail, but I said let's compute the capacity of a, or I'll make it full screen. So let's compute the capacity of a W21 by 44, assuming it's 10 foot long and that it's pinned on both ends. Let's compute the column capacity of that, the capacity and compression. So what I did essentially is I looked up all the necessary properties for a column, and then I did that classification exercise, and I found I had a compact flange, but I have a slender web, okay? So this column would experience local buckling about the web. So we can't use directly the same stuff that we did for columns. We have to adjust it a little bit, and we do this according to section E7. So I will go through this in a little detail. So largely what you end up doing is you use a lot of the same equations that you did before, but you end up tweaking them a little bit. So the first thing that you do is you compute your KL over R, your FE, you figure out what FCR expression you got, and you do that. Okay, but then what you ultimately end up doing after that is you reduce the area. So the idea is that you have an I shape, right? And if you're computing the capacity, you basically say some of that web is ineffective because some of that web has buckled. So we reduce the area based on how much of the web is buckled, and that's our capacity. So what you do is, I'm not including those tables in the manual here and here, because the idea is that you could take this, open up your manual, and sort of follow along the manual where this is going. But basically what you're doing is you're computing some adjusted buckling stresses and ultimately trying to reduce the area. So you basically compute an effective area, which is cutting a little bit of the area out to account for the fact that some of the web is buckled. When it's all said and done, you get a capacity of 294.3 kips. You can actually verify that if you look up the capacity. You'll find that if you have a column length of 10 feet, look up the capacity, you get the same length or the same capacity as if you computed it. So really the point of this week, I guess I kind of fibbed a little bit because I said, this week we're tying up loose ends. Tying up loose ends mean covering shear and covering local buckling. But I also kind of want to somewhat prepare you for design outside of what we learned directly in this class, because there's going to be problems that you deal with in the real world where, okay, in Dr. Mike's class, we learned how to just do LTB, but we didn't learn how to do it if the flanges were non-compact. Well, how do we do it? It's not hard. Just, follow the manual, read it, go through the specifications. I mean, the specifications are designed to help you out. They may seem daunting, but there's been a lot of care taken to ensure that they're well organized, they're easy to follow, the math is pretty straightforward. Another thing that's also been done pretty well, at least with American design specifications, is that if you open up the bridge specification and open up this, which is the building specification, and look at the models and equations for plate girders and the same ones here, they're all pretty much the same. So there's nothing that for the most part, there's nothing that you'll find in the bridge spec that's grossly different than what's in the building spec. There are some tweaks. So like the CB equation that you use in the bridge spec is a little different than the one you use in the building spec, and a couple of other things, but by and large, it's all pretty much the same. Because the idea is that as an engineer, you don't need to be juggling with that while you're designing different components. Ultimately, the steel beam doesn't really care what it's going to be used for. It should behave the same way it's going to behave. So. Any questions? Would you like to get out at least 5 minutes early? Yeah, 5 minutes early. Would you like to get out early? Here's what I'm going to do. I'm going to pull up the QR code one more time. You got one final homework for me. Classifying a W14 by 43, and that's all I got. I will see you all on Friday for exam review. Be prepared with questions.
No questions.
Well, I'm asking you questions next week, so you know. All right, see you.